Hey everyone, and welcome. So, we're literally surrounded by solids all the time, right? But have you ever stopped to think about what's going on inside them? Because it turns out, hidden in these materials we see every day is this incredible world of order, chaos, and a puzzle that honestly changes everything.
And to get to the bottom of that puzzle, we're going to look at one of the most famous paradoxes in the entire material world. It's a tale of two substances made from the exact same ingredient that just could not be more different. I'm talking about the carbon conundrum.
Okay, let's just dive right into this. You've got diamond on one hand, and on the other, you have the graphite in your pencil. Here's the crazy part. They are both pure, 100% carbon. So what gives? How on earth can the exact same element create both the hardest thing we know of and something that just flakes away onto paper?
And the differences, they're not small. They are absolutely extreme. A diamond is so ridiculously hard it can cut steel. It's crystal clear, transparent, and it won't conduct electricity at all. It's an insulator. Meanwhile, graphite is one of the softest minerals out there. It's dark, opaque, and it's a fantastic electrical conductor. They are total polar opposites.
So to solve this, our very first clue lies in how the atoms inside a solid are actually arranged. It turns out that pretty much all solids fall into one of two major camps, the ones that have a deep sense of order and the ones that are, well, just pure chaos.
So on one side, you have your crystalline solids. You can think of them like perfectly organized soldiers, all in formation, a perfect repeating three-dimensional pattern. And because of that order, they have a really sharp, specific melting point. Then you've got the amorphous solids. Here, the atoms are just a jumbled, random mess. And because of all that disorder, they don't really melt at one temperature. They just get softer and softer as they heat up.
And to make this super real, just think about table salt, or diamonds, or really any piece of metal. Those are all crystalline. Now think about something like glass, or wax, or a piece of plastic. Yep, those are your classic amorphous solids. And our two mystery materials, diamond and graphite, they both fall squarely into that first group, the orderly crystalline camp.
Okay, so wait. If they're both crystalline, that can't be the whole answer, right? The clue must be buried deeper. We need to zoom in and look at the actual atomic blueprint, the specific way these super orderly solids are put together.
Every single crystalline solid is built on a framework that we call a crystal lattice. You can't see it, of course, but it's this incredibly precise underlying structure, kind of like an invisible scaffolding that holds every single atom or molecule in its exact right place.
And if the crystal lattice is the entire scaffolding for the building, then the unit cell is like a single Lego brick. It is the absolute smallest piece of that lattice that, if you just copy and paste it over and over again in all directions, builds the entire crystal. It really is the fundamental building block.
And it's really that simple, conceptually. The entire massive structure of a perfect crystal, doesn't matter if it's a tiny grain of sugar or a huge diamond, it all comes from taking that one tiny unit cell and just repeating it trillions upon trillions of times to form that perfect lattice.
All right, let's pause for a second. We have all the pieces now. We get that solids can be ordered or chaotic, and that the ordered ones are built from these tiny repeating unit cells. We are finally ready to crack this carbon mystery wide open.
So here it is. This is the crucial point. It was never about the fact that they are both made of carbon. The entire secret, the whole reason for their wildly different properties, is all about how those carbon atoms are connected to each other inside their crystal lattice. The type of bond, that changes everything.
You see, crystalline solids kind of have four main personalities, and they're all defined by their bonding. You've got ionic solids like salt, you've got metallic solids like copper and iron, and molecular solids like ice. But the one that really matters for our story today is that fourth type, covalent network solids.
Diamond is the ultimate covalent network solid. It's the poster child. Inside its lattice, every single carbon atom is grabbed onto four other carbon atoms with these incredibly strong connections called covalent bonds. There are no weak links. It's basically one single, gigantic molecule all locked into a super rigid 3D grid, and that is the source of its legendary, unbelievable hardness.
But graphite? Oh, graphite is the brilliant twist in the story. It also has those strong covalent bonds, but here's the catch. They only form flat, two-dimensional sheets. Think of them like atomic-scale sheets of paper. The atoms inside each sheet are bonded tight, but the sheets themselves, they're only held together by really, really weak forces. And that's it. That's why they slide past each other so easily, which is what makes graphite so soft and slippery. Mystery Solved. So, there we have it. The arrangement of atoms totally defines what a material can do. But okay, why does this matter beyond just being a really cool science puzzle? Well, it matters because understanding this is basically the foundation of almost all of our modern technology.
And, here's the final twist, which I just love. In the real world, a perfect, flawlessly ordered crystal, it's almost useless. It's the tiny mistakes, the missing atoms, the little impurities, the imperfections in the crystal lattice that we can actually control to give materials all the amazing properties we rely on every single day.
I mean, think about it. The silicon chips that power your phone, they only work because we intentionally introduce impurities into their crystal structure. The alloys that make steel strong enough for our bridges are just planned imperfections. Even the beautiful color in a ruby or a sapphire, that's just a tiny impurity in an otherwise clear crystal. We have literally engineered imperfections to build the world around us.
So the next time you see a diamond sparkle or just use a regular old pencil, I want you to remember this incredible story of atomic architecture that's hidden just beneath the surface. We've built our entire modern world on manipulating the solids that we understand. And that just leaves one final, huge question. What are we going to build with the ones we haven't even invented yet?